Bismillah Rahman Rahim. Assalamu alaikum everyone. We are going to start a new tutorial series about analog to digital conversion in microcontroller. So first of all, we need to know what is analog to digital conversion and why it is needed in microcontrollers or microprocessors projects, right? So for this purpose, I have considered a typical example in which a microcontroller uh, is shown, and there are two sensors. One is temperature sensor, another is pressure sensor attached to this microcontroller. We are aware that temperature or pressure both are physical quantities, so their results will be physical or results will be analog. And we know that microcontroller is a digital system device or is an application of digital systems. So it is a device which understand only digital language, while these two sensors which are shown here, they can be analog and they can produce analog data, right? Because although there are sensors now available who are digital themselves, but still we are talking about a general scenarios sensoring system. Sensors are usually analog because in analog nature they can process their information faster and they can actually deliver more accurate results, right? So generally sensors are analog, but we know that this device is digital. So if these pressure sensors or temperature sensors are attached to this device, then this device won't be able to understand these signals which are coming from these sensors, right? So what do we need here? We need here something which is known as ADC. What is ADC? Analog to digital converter, right? Now it is quite there are two scenarios that either this microcontroller has a built-in ADC or a separate ADC need to be connected with this microcontroller. And what is the purpose of this microcontroller? It will convert this analog information or this analog data coming from analog sensors into the digital information, right? So that it can be processed by this microcontroller. Therefore, ADC is very important tool within the microcontroller domain, which enables microcontroller to understand physical or analog signals. So in this tutorial, we are going to talk about ADC and what are the important ADC terms which must be known to programmer or must be known to microcontroller students who wants to implement their physical sensors with microcontrollers. So we have already talked about the analog to digital conversion and its purpose in microcontrollers projects, but still there are some terms which one need to know before he or she is going to implement the analog to digital conversion. So in this video, basically we are aiming to discuss all those important terms and terminologies which are very much relevant. And if you are going to learn about analog to digital conversion, then this is a simple guideline or a basic guideline for you guys, because if you are aware about these terms, probably you won't have any understanding issues or you won't have any technical issues, because you will be going with the concept underground which must be needed to implement analog to digital conversion. So what are the terms I'm going to talk about are basically listed here. I'm going to talk about resolution, the reference voltage, the step size, serial versus parallel ADC, multiple analog channels, conversion time, or SC and EOC signals. These all are important steps and important terms. If you are aware about it, you are very good to go. So let's start our terms one by one. What is a resolution? You know that whenever we talk about analog quantity, uh, it has a continuous change in magnitude, right? But this is not true for digital. For digital purpose, we will have number of magnitudes or discrete levels. Those are called resolution. So number of digital bits which are used to represent the analog quantity is known as uh, resolution, right? For example, if we are going to use, let's say we are going to use 4-bit converter, so we can say that the minimum value would be about 4 times 0, and the maximum it can go up to 4 times 1. So this is called the resolution. And this is something which is very useful. The more number of bits you have to represent the analog data, the more accuracy you will have. Lesser the number of bits in resolution, lesser the accuracy of ADC conversion. So this is why it is very critical and it's very important as well. Furthermore, if we talk about resolution, in resolution we will have nowadays microcontroller may come in 8-bit, 16-bit, 24-bit form. So they may have 8-bit, 16-bit, or 24-bit resolution of ADC. But since we are going to discuss this perspective in terms of PIC18F, so PIC18F and PIC18F is an 8-bit microcontroller, so it might have 8-bit or maximum 16-bit ADC resolution, but we are going to talk about specifics in coming tutorials or later in this tutorial as well. So what is the next thing about resolution? This is fixed. Yeah, it is something which is very, very important to understand. It is kind of fixed. You cannot change it, right? It is fixed at the time of chip design. Whenever microcontroller chip design was in design procedure, or you can say the ADC chip was in design, it was the moment you can decide it. So designer have already decided it for you and it is fixed and you cannot change it. But in some microcontroller, you may have multiple resolution options. So you can choose one of them, but you cannot change it, right? So this is very important point from the programmer point of view, that he need to know whatever the microcontroller he is using, he need to know what kind of resolution or what number of resolutions are available in that specific microcontroller. Okay, next thing about resolution, though it cannot be changed, resolution cannot be changed, but its step size is something which is very, very critical in ADC conversion. For those who are not aware about what is a step size, I'm going to tell you in very nutshell. For example, this is a analog signal and we are going to digitize it, right? So we are going to divide it in number of levels. This is the concept of journal ADC. Soon I'm going to continue some other tutorials specifically about analog to digital conversions, which will not related with any specific microcontroller as these tutorials are. So I will cover these concepts further in detail, but right now I'm giving you a nutshell idea. So basically, a complete analog quantity is going to be described in digitized number of levels and the space between, right? For example, you can say that this is the point which is exactly equal to the analog. This is the point which is exactly equal to the analog. But what about this position? This position is not found. It's not found in any of the discrete level. It is not equal to this level. It is not equal to this level, rather in between of them. But once you are going to digitize it, that means you are going to miss this point, and that point is called step size error, right? So the smaller the step size, you will have less number of errors. But if you increase the step size, you can actually have a variety or huge amount of error. So this is something that you can actually decide, or step size can be adjusted. And how you can adjust it, let me tell you what you will do. Step size, I'm going to speak about it, how you can change it sooner. I'm going to show you some example of it. But first of all, let's talk about some time which is called conversion time. It's very critical. It is another term. The first term we learned about the ADC is resolution. The next important term is conversion time. How much your ADC IC or ADC chip takes to convert an analog signal into digital form. That is called conversion time, right? So if you, this is what I have described here, time taken in conversion, and conversion means procedure of ADC. The next thing, okay, it is dependent on clock source. Why it is dependent on clock source? Because clock source provides the basically sampling frequency as well, which is very critical in ADC. So I hope since you are following this tutorial, you already know about what is ADC, what are the basic concepts. Like I told you, there is a step of quantization, there is a step of sampling. So in sampling, so sampling frequency is very important, and sampling frequency is driven by or dictated by clock source, especially in PIC18F or generally microcontrollers, right? So next thing which is related with conversion time is conversion method. You know that research has been going on ADCs and on technology, and every day we come across with a new invention of methods. So there are several kind of methods available in general idea of ADC. So it also depends, yes, that how much your microprocessor is latest and it is using the latest technology. So conversion method is also important, but it is something which should not be the case, or which should not be the bothering case for the programmer, because programmer is totally unaware about this conversion method, right? But once if you are choosing a microcontroller and you are choosing it for ADC conversion, so you must read about conversion method, what kind of conversion method and how efficient conversion method are being used in a specific microcontroller, right? So conversion time is also function of conversion method. Okay, this is another important IC technology like TTL or CMOS. We know that there are various kind of combination logic available, transistor to transistor, or CMOS, which is field effect transistors, ICs, right? So fabrication method of ICs also translates into conversion time. Faster your technology, faster will be conversion time. Slower your technology, slower will be, I'm not your, but your microcontrollers technology. So slower your conversion time in ADC. This is something which can be boring for those microcontroller programmers who are actually listening this lecture about the programming stuff. But this is something which is very relevant, because if you are not aware about these basics idea, you can't program the efficient ADC. That is why I'm including this stuff in this video series. Okay, next thing we need to talk about is V reference. V reference is also known as reference voltage. You know that if though you are converting an analog signal into a digital form, but still a digital signal needs to be corrected itself with reference of certain voltage, and that voltage, that input drive signal is known as reference voltage. And we are going to see some numericals here. For example, so this is the input voltage. Of course, it will be given by the programmer itself, and then it coordinates with chip's resolution, which is very important point. V reference coordinates with chip's resolution. Remember, chip's resolution, it can be 8-bit, it can be 10-bit. The number of bits you are using to dictate or display your digital output. So this is very important. They are coordinating themselves, V reference and chip's resolution, to decide what step size is. As I told you, I'm going to talk about step size. So this is the time. So how step size is calculated is an example I have just covered. If you are interested to use, this is example, and if you are interested to use 0 to 5 range of voltages, right? So this is basically, you can say 0 to 5 volt range, right? With 8-bit resolution. So you can see that the concept is very clear. 8-bit resolution, this is our bit resolution, and this is the maximum voltage, or the range, or the minimum and the maximum. So if you are aware about ADC basics, then you must be aware their minimum and maximum voltages are important. So maximum voltage is basically kind of V reference. That is why it is important. So the step size can be calculated as I have calculated here. Step size equals to what? V reference, whatever the maximum voltage, divide by 2 power n. N is what? The bit size. So here bit size is what? Or the bit resolution. The resolution is what? 8. So 2 power 8. That is why V reference divided by 2 power 8 will become the step size formula here. And we know that the maximum voltage is a V reference voltage. So 0 to 5, the 5 is the maximum figure. So 5 will be divided by 2 power 8, and 2 power 8 is what? 256. So if 5 will be divided with 256, it will become 0.019. And eventually you can also write it, since we are talking about voltage. So step voltage, or the size of step for which digital output will vary in terms of magnitude, it will be 19 millivolt, right? 0.019 was some significant figure, and I just converted into normal form. So 19 millivolts. So 19 millivolt is a step voltage or step size of this ADC. I hope this point is clear. This is very critical. You need to calculate whenever you are comparing or converting any analog technology, any physical or analog quantity into digital form. You need to calculate its physical size. You may You may be given with certain, for example, temperature, pressure, or any other physical quantity, but you always need to decide first of all your reference voltage, and then it actually help you to decide about step voltage. Next thing is D out. D out is something which is most importantly for which we are doing every this rubbish stuff, digital output. Whatever the analog signal you are giving, whatever the physical signal you are providing to your ADC chip or microcontrollers ADC, you are interested in its output, and that is called digital data or digital data out, right? And that is basically the number of bits. As I told you, if it is 8 bits, so you will be given with 8-bit output, right? If it is 10 bits, so you will be given 10-bit output, right? So it is a digital output of ADC. This is why it is very important, and you need to know how to derive it. For example, if you're considering a 8-bit ADC, so you will have an 8-bit ADC output. That means you will have 8 bits, right? Starting from D0, D1, D2, D3, and I go up to D7. Similarly, if you're talking about 10-bit ADC, that means your output will vary in terms of bits from D0 to D9, right? So this is very important and critical thing. You need to understand your digital output pattern. Okay, the next thing, D out. Okay, this is something very important. How you will calculate D out and how it is related with the step size and input voltage. Remember, right? So once you have calculated your reference voltage, you have decided your reference voltage, you have decided your resolution, you have eventually calculated your step size, as in last example I did, or in last slide I calculated it for you. So basically now we are interested in Veen. So whatever, for example, 0 to 5, if you remember my example, the range of the signal was 0 to 5. So basically my input signal can actually be 0 minimum, or maximum it can go up to 5. So it can be 1.25, right? Or it can be simply 3, or it can be 4, or it can be 3.75. So any input signal which is applied on analog pin, it must be calculated in digital stream, right? In digital output. So this can be done using this formula. What you will do, what you will actually calculate, so you will divide your input signal. For example, it is 4, you will divide it 4 with 19 millivolt. Step size was 19 millivolt in this example, as I explained in the last slide. I hope you know it. So okay, again I'm taking an example. So this time your input voltage is what? 4.5 volts. So I'm expecting 4.5 volt is input volt, and it resolution is around 8-bit. Step size I've calculated 19 millivolt. So if I'm going to calculate or going to perform this calculation, it is going to be this, right? If you are keen and observing it, 4.5 volt divided by 19 millivolt, it becomes 23.6.84, and approximated it is equal to 237 in decimal. And if you are going to convert into binary, since it is 8-bit, so it becomes 0001 110 1101. So it is an 8-bit form. Remember, this is the specimen example. You can take any other input reference voltage. For example, you can take 3 volt, you will divide it with 19 millivolt, you will have a digital display in decimal numbers, and then you approximate it and convert it into 8-bit form. So this is how your analog to digital conversion is performed as far as your PIC microcontroller or microcontroller ADC chips are concerned, right? But remember, this is something manually we are doing in this lecture for you, but this will be done by the chip itself, right? So this is the output we expect if we are given with these circumstances, okay? So let's move to the next. Okay, this is something very important. These digital output can come into CPU serially or parallelly, in parallel mode from the ADC. Remember, I told you CPU itself is not performing this task of ADC, right? This task is performed by ADC chips, which are either built in your microcontroller, or they are outside the microcontroller. But remember, if CPU needs these digital outputs, so he will ask these ADC chips to perform this ADC conversion, and then ADC conversion is performed, and then that output will be sent to what? Back to CPU, because it is the CPU who was interested in those digital outputs, right? So there is a two type of variation. Either the digital data can come serially, that means bit by bit. I have already covered about serial communication. so many tutorials in PIC18F point of view, so you can follow those tutorials. And then there is also concept of parallel mode, though we haven't covered any parallel tutorial, but you know that parallel mode will be more faster and more easy to implement, but serial will be more slower but more efficient to implement, because it won't consume or it won't utilize more hardware, right? So this is something which we are going to see in a while, how this serial and parallel communication, or how this affects, or how it introduces new terminologies in ADC conversion of microcontroller. Uh, uh, okay, let's move into the next step. Okay, the next thing, okay, this is very important. This is very important slide, because in parallel ADC we have multiple D out pins. D out pins means digital pins, digital output pins, right? Coming from ADC to CPU, right? For example, ADC 848 is a specific multiplexer or specific ADC chip, which is basically which performs ADC and sends the output pins in form of 8 pins parallelly. Okay, what if we are performing serially? Serially, we have only one D out pin. As I told you, we will use only one pin as an output pin. So that means there is a built-in parallel shift register built in inside that chip, and that will be converting that 8 pins or 10 pins or 12 pins or 24 bits into single bit, because that parallel shift register will send bit by bit information. Furthermore, there is an example of Max 1112, which is very well known and very famous ADC chip. Can be bought and can be purchased in usual markets. Normally, digital electronics students or electronics students pass it and use it in very projects. So basically, this is a very simplest example of serial ADC. Okay, as I told you, to save wires and space, higher resolutions ADCs are used. But if higher resolution, you know that there are, for example, if I say that I'm using a 24-bit ADC, that means these we have only 8 bits, right? And we are using 24 bits. So what is going to happen in 24 bits? They are going to divide into 8 bits form. So first 8 bit will transfer through D0 to D7, then next 8 bit, then next 8 bit. So this is how you can actually save the wires and space and complexities into the ADC. Okay, as I told you, in case of 16 bits, it will first send lower bytes and higher bytes. I have already explained these things. Okay, this is something very critical. Okay, first of all, we need to clear it. Yes, analog input channels. You know that in various applications, we don't need only single physical quantity to be converted into digital form. Rather, we need many physical quantities to be converted into digital form. For example, if one is following and observing temperature, pressures, wind, so there may be various sensors attached to the microcontroller project or microcontroller application, which are sending analog data, and you need to convert them and manipulate it according to your need. So there are various analog input channels available, right? That means you will have number of input channels. For example, if you remember my example, I converted for 4.5. So there is also another channel from which you can say that 3 volt is coming. There is another channel 2.5 volt is coming, because they are coming from various channels, from various sensors, right? And you can actually convert any of those channels into your you can take them as input to your chip, and chip will perform your ADC and out the pressure or out the digital form, right? So this is something you need to understand, that there are various microcontrollers which support various analog input channels, and they can be selected, right? So what next? There are multiple channels for this purpose in several microcontrollers, but a very important point. Okay, this is the same stuff as I already explained you, simultaneous temperature pressure monitoring. Okay, the important point I was talking about is this one: start conversion and end of conversion signals. This is another, and I think probably the last important thing that I'm going to talk about in this tutorial, that start conversion and end of conversion signals. What are these signals and why do we need it? As I explained you in the last slide, that we have various multiple analog signals. So we need to know what channel is selected, right? We need to know if the select channel is selected, then other channel cannot be accepted, because once one channel is already in progress. So that means we need some signaling method that is called start channel or start conversion or SC signal, and end of conversion or EOC signal, right? What are those? Let's see. As I told you, there are multiple channels are coming, coordination is needed, and for that coordination we are going to use this signal. So what is a start conversion signal? What is end of conversion signal? Whenever microcontroller chooses or selects a specific analog channel to be converted into digital form, it posts a LED, or it starts an LED, or it starts a signaling with this channel, with this signal, start conversion signal. Whenever this signal is high, that means conversion has already started, right? Or you can see that after the selection of the channel, it first of all, microcontroller governs this signal or give this signal to indicate their conversion is already started. And so no more analog signal is accepted, because once already an ADC conversion is in progress. And after the end of the conversion, right, once your ADC conversion is finished and your digital output is ready, so there must be a signal which dictate you that your conversion has been performed. So there is a signal which is called end of conversion signal, which indicate that your ADC performing, or your ADC conversion has already been completed, right? So these are the two steps. Okay, if I'm going to summarize all this stuff in four simple steps. So first of all, the first step is select the analog channel. So you need to actually select the first channel first, right? So you will select your analog channel. The next step is you will activate the SC signal to start the ADC process on selected channel. The next step is we have to keep monitoring for the EOC channel, or for EOC signal. That means end of conversion signal, right? And the next step would be what? Once EOC signal is activated, then we have to read the digital output. That means our final output of that selected analog channel in digital form is ready and we can read it, right? So these are the basic 4 steps that one need to follow. Okay, that's it from this video tutorial. We have learned about what are the basic steps and how ADC conversions are performed in microcontroller, specifically in PIC18F microcontroller. In coming tutorial, I'm going to speak about some other important steps of assembly language programming or other register which are related to this analog to digital conversion in PIC18F microcontroller. So still, if you have any confusion in understanding of these basic terms of ADC in terms of PIC18F microcontroller, you can post your queries in comment section. Thank you so much for listening.